that has m of x in it. Now I'm going to have an m dot term when I take my time derivative, my Lyapunov function. And so I need something to cancel out with this m dot term. So forget about that property altogether here. Okay, just think of it like I've got that sitting there. What can I do to get rid of it? Okay, and so what I did is I just came in here and I said, well, this is what that term is. I'm just going to add and subtract it. So I can inject a term that will exactly cancel it. Okay? And then, so it actually worked out that the plus term is what I needed to inject to cancel it. And then the minus term, I could just include in my y theta. Is that clear?
Yeah, I understand that part. I actually don't understand is where you actually got m sine x dot.
Oh, m x dot times x sine x? This term?
Oh, okay.
This came from the dynamics of the system. This came from up here in our dynamics.
So really what we're doing is making things up as we need to in order to show that everything goes to zero.
That's exactly right. That is the Lyapunov-based design method. You know, you're given some dynamics, you're given some error, some objective that you quantified mathematically, and then you're just thinking, you know, well, I've got this skill set that if I had this positive thing over here and I can show its time derivative is negative, then I can start talking about the stability of things. And so what stuff can I throw in the trunk to make it all work out in the end? And it's not by doing anything fancy here, by choosing some magic Lyapunov function, like a lot of people are concerned about. Why do I know how to pick a Lyapunov function? It's, you know, 1/2 r squared. There's not a lot of magic there. But where the creative process is going back and forth between the error systems and your control design and the stability analysis. Just going back and forth, back and forth. All right, well, that didn't work, so let me try this thing. And I throw this in the closed-loop error systems, and now I plug it in my Lyapunov analysis. And, well, that got me a little bit further, but doggone it, now I've still got this other term sitting there I have to take care of. How am I going to take care of that term? And so it's just back and forth, back and forth. Good. All right, so if there's no more questions, we'll go on to our backstepping example.
Now we really don't know, again, I mentioned before, we don't know what's going on between time zero and stability. This just tells us it's stable.
That's right. That it says our errors are going to zero. But so if I were to continue this analysis, I would have v dot is equal to minus kr squared. And so I know that r is a member of L2. So this means that the integral of some gain times some signal squared has to be less than infinity. So if r squared were 1 or 1/2, this would go to infinity, right? So even though we don't have like a nice envelope where we can talk about percent overshoot and critically damped and things, the fact that this is L2 means it's going to zero pretty fast, or else it's going to blow up, right? Because this has to race towards zero, or else it's just going to be an enormous term. It's going to blow up to infinity. So it does give a sense of the performance, but it's a loose sense. And it's an unfortunate drawback of nonlinear control, which is an unfortunate drawback of not being able to solve the differential equations.
But generally they follow that quickly with stability.
Yeah.
Is that a kind of integral?
Yeah.
And if you wanted to slow down as far as when it gets to stability, if you wanted to control its rate of going to stability.
Well, as R gets smaller, then you've got your control gain multiplied by a smaller and smaller and smaller and smaller number. So it slows itself down a little bit. So these are all good questions. Anybody else have any questions? Okay. All right, so let's go on to backstepping. Well, on my way over here, I walked by one of those buses, and it had on its little "Where It's Going" sign was Oaks Mall, and I just dreamed. I said, well, wouldn't it be nice just to get on that bus and go shopping and not have to go to class, answer a bunch of questions and do a bunch of algebra? It would be good. So we were doing our robot example. And we got halfway through, and it looks like we'll probably get about halfway through again today. So if you remember, we had x dot equals j of q, q dot. And I'm fairly confident everyone in here has seen that equation before. It's the robot kinematics. You can call it airplane kinematics if it makes you feel more comfortable. And we also had the dynamic model, mq double dot, m of q, q double dot, plus vm q, q dot, times q dot, plus f of q dot, plus g equals torque. This was our dynamic expression. And we said our objective was to drive x to xd, and so we defined an error signal as E equals x minus xd. And we said that this was a cascaded system, right? That this is the kind of system that when we see it, red flags should come up immediately that says backstepping, backstepping, backstepping. Because here's my equation with my control effort in it, my torque, right? There's nothing but q dots and q's in there, right? But my control objective is in terms of x. So we said this was the joint space, this is the task space. So what does one do in this kind of a situation? Well, luckily we have another set of differential equations that relates the q stuff to the x stuff. Okay? So we have a cascaded system because if we can, and the way to think about it is, if I can design the torque to make the q dots do a certain thing, then I can make the q dots control the x dots and make the x's satisfy my control objective. And so we said that maybe a clearer way to think about that is to use backstepping. We define a backstepping error, and that was at QD, okay, Q dot minus QD dot. And then we say, okay, well, I'm going to start with my non-actuated dynamics, and I need to insert a phantom controller in there. You guys ever watch Danny Phantom? It's on the Cartoon Network, I think. My son likes Danny Phantom. So then I've got x dot equals j of q times q dot. Here's my old add and subtract trick that II doesn't like me doing. J of q, qd dot minus j of q, qd dot. Okay, and now here's my minus j qd dot, my plus j q dot. So those are equal to j of q times eta plus j of q times qd dot. Where I've got my backstepping error signal in there. And now I've injected this QD dot term, which is my phantom controller. So it's my desired joint velocity. So if I were king for a day, how could I adjust the joint velocities? Is there a way I can adjust the joint velocities, the Q dots over here, to make the X thing do what I want it to do? That's the question. Okay, so we have this air system, our backstepping air system. Well, no, that's not the backstepping air system. That's just our state air system. And we said, well, okay, X dot equals J of Q eta plus J of Q QD dot and I said my control objective, so I did a change of variables here from X to E, where I went from X to E of X comma T. And so I said, well, what does E dot look like? Because I'm going to want E in my Lyapunov function, because I'm going to want to show E goes to 0. If E's in my Lyapunov function, I'm going to have an E dot that I need to be concerned about. So let me look at E dot. Well, E dot is just equal to X dot right here, J of Q eta plus J of Q QD dot minus XD dot. And in this particular example, we said, for simplicity, let's just let XD be a constant. We're going to drive it to a constant position. Okay, so since XD is a constant, then XD dot is 0. So now I'll look at this, and I'm going to assume, I always hate writing that word down. Roger loves this word. Roger would write a whole paper with just, I assume the control objective is satisfied. Right? That's just one assumption. All right, assume QD dot. No. Assume J of Q is non-singular, meaning the inverse exists and is bounded. Okay, so then I can design QD dot as equal to J inverse. Let's get rid of that thing we don't like sitting there. And we said before that we're going to let the backstepping air kind of float through, right? Because we're going to have a eta dot and an eta in our, we're going to have an eta in our Lyapunov function. We're going to have an eta dot, and we could probably just cancel that term out with our torque. So let's just let that float through. And so we'll have J inverse times minus KE. What's that Edgar Allan Poe poem that where he cut out the guy's heart and buried it under the floor? And then just heard the heart beating all the time. You guys know that? The telltale heart. It's like the telltale bell in here. It's that bell. You know, I'm just waiting for it to go off because it means I can't talk anymore. We're going to have to continue it again. Another class. So I get E dot is equal to J of Q times eta minus KE. Okay? Why did I do this? Well, I always know I want this feedback term. Those give me the warm fuzzies. And I'm kind of working on a leap of faith here that the professor told me that it was okay to let the backstepping air just kind of float through the analysis. Well, we'll see. If it doesn't float through the analysis, maybe we'll have to do something about it. But it would sure be hard, right? Why would it be hard to take care of this eta term? Well, what is eta a function of? Eta is a function of Q dot and QD dot. What phantom input do I have that I could use to take care of eta? QD dot. Uh-oh. It's sitting right there. So even if I wanted to, I'm not going to be able to use QD dot to get rid of eta. Okay, so this is my open loop. Oh, this is my closed loop air system for my aerodynamics. Now I need to develop my open loop and closed loop dynamics for my backstepping air system, which is going to be my eta dot kind of term. Okay? So please put a gold star by this equation, and on Monday we'll pick up from here where we've got this air system already developed, and then we'll start working on this eta dot air system, and then we'll finish this example in backstepping. And then I've got a nice backstepping problem for you guys to work on your own. Any questions?
Where did QD dot come from? Is that by design or is that?
QD dot? Well, I just looked up here. I don't like the JFQ, so let's get rid of that immediately. And then I'm going to leave this one, and so I need to inject a air feedback term to get my E dot equals minus KE kind of term. So that was the motivation for designing it that way. Any other questions? Okay. So you guys please email me your grades. Only 2 or 3 of you have done that.